Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's really great to see you all here, and it's really a great pleasure for me to introduce our first keynote speaker. Some of you know me, I'm really attracted to quotations, and I thought there was one by Sir Winston Churchill that really fits our first speaker and his topic of his talk this morning. True genius resides in the capacity for the evaluation of uncertain, hazardous, and conflicting information. Seems like it could have been written by our speaker, Eric Horvitz, this morning. Eric is, in fact, one of the world's most important researchers on problems and ideas and principles related to sensing and decision-making under uncertainty. He is, of course, for his distinguished research contributions and career, a member of the National Academy of Engineering, a AAAI fellow, a fellow also of the American Association for the Advancement of Science, and the other AAAI, the American Academy of Arts and Sciences. Besides really amazing and important, long-lasting research contributions, Eric is also an amazing mentor to many, many young scientists around the world, some of whom are now not so young. And a servant to the community. He was the immediate past president of the AAAI. He is on the advisory committee for the NSF Computer Science Directorate and a member of the CCC Council. And last but certainly not least, the deputy managing director for the Microsoft Research Lab here in Redmond. And for that, I'm really grateful because, of course, we work extremely closely together. And so please join me in welcoming our first keynote speaker, Eric Horvitz. Eric?
Well, thanks for that very nice introduction, Peter. So it's certainly, we're in incredibly exciting times. I have to pinch myself once in a while when I put myself back in my grad school days at Stanford in the mid-'80s to late '80s to think about the computation and memory we now have, the connectivity and data, and most of all, the learning and reasoning algorithms we now have to work with data, make decisions under uncertainty, and so on. And I thought today I'd talk a little bit about some opportunities and directions in this realm. Back to my late '80s at Stanford, we were really excited about this idea of capturing uncertain expertise with graphical models, Bayesian networks, where these random variables represented as circles here are connected to other random variables with these arcs that represent dependencies. And this took us, a team, Ingo Beinlich and others, about 2 weeks to build by hand, where the numbers came out of the mind of an expert anesthesiologist. And once we built this network, this graph, which represents distinctions you worry about in ICU, intensive care medicine, you can run them by putting any observation in here, blood pressure and CVP, things you could see, running Bayesian network algorithms and picking off probabilities of things you couldn't see, like pulmonary embolus. So these are very exciting graphs, but they were very time-consuming and hard to build. Now, in the 90s and into today, there's really been an explosion of learning methodologies to learn these kinds of graphs from data and learn other kinds of models as well. Here are 3 variables, and you can connect them up in a variety of different ways. And one approach called Bayesian structure search basically looks at all the different combinations using heuristics to form these structures and has a score to score the power of that model to explain data and finds the best model. And that model typically is the one you use to actually go out and actually make predictions in the world of these states you care a lot about that you can't usually see directly. And of course, there are other procedures as well. Beyond making predictions captured here by this little histogram here from data, we also worry about actions in the world, in the open world. What happens when you base take preferences and these uncertainties that are inferred from these models and take action. And so the set of innovations has been marvelous in the space of going from predictions to actions as well. In fact, I like to think about a data to prediction to decision pipeline often. A couple of exciting directions. First of all, this idea that all of a sudden, based on connectivity and communication systems, we have these ambient, you might say, in-stream data resources that just are available. This hit home for me a few years ago when we got access to a cell phone data set that just basically had densities of cell phones at different towers in Rwanda. And Ashish Kapoor and I are working with Nathan Eagle looking at what we can say about what happens to these cell towers and communications more generally when there's an earthquake, about a 6.0 earthquake outside of Rwanda, not far away, the Lake Kivu earthquake. And about 10.5 million phone calls, watching the anomalous calls on these cell towers, only 140 of them from this earthquake, led us, with some interesting probabilistic methods, pinpoint within a few kilometers of the epicenter, just by watching the surge in phone calls at different cell towers as people responded naturally. And we could take a decision model on top of that and compute regions of the country we'd want to do surveillance on, reconnaissance, because of standing disruptions based on the uncertainties there, just from ambient data. But among exciting technical directions in learning right now are causality, really getting to the foundations of core science. Does A really cause B? Or do A and B co-occur with a cause upstream called C? Active learning, thinking a lot about how we can grow a database given the costs and benefits of collecting data. Lifelong learning, building systems that really understand that they're being used over a period of years to decades, and serving a population of people, for example. And then recently, this is technical work in deep learning. This is like you might call this the third wave of neural nets, where the idea of a neural network that's biologically inspired has been a long-term dream, and it's been at foundations of intuitions. But recently, we're seeing notions of taking these multi-layer or cascades of networks where we build inferences at one layer that become inputs to the next layer and so on. And we're actually seeing significant gains, which are actually surprising and give us the sense that maybe there's something to be said about looking very carefully at this third wave of neural nets. Lots of interesting directions going on there. So today I thought I would focus on 4 efforts at Microsoft Research, several of which are developed closely with our partners at several universities and other government agencies and centers in transportation, healthcare, citizen science, and then some hard problems we're facing in trying to build and address the dream of integrative AI, or long-term dream of building intelligent systems. And I think for each one, I'll capture some themes that I think are interesting to this group. And I chose some societally relevant topics. I think people will resonate with them. They also resonate with some of the work that the Microsoft Research Connections team has been funding over the years externally. So first, in transportation, I wanted to stress this work, which is going on for about 7 or 8 years now at Microsoft Research, highlights the notion of the power of heterogeneous data sources and user models. So about 5 or 6 years ago, we were very interested in the Seattle traffic problem. Everyone from Seattle knows that we have the worst traffic in the world. I thought the Bay Area was bad until I got up here. So we started looking at sensors in highway systems. We can get multiple views on traffic from the highway systems. We can get incident reports from the Washington Department of Transportation. Like Nick here is reporting on what's going on in terms of lane coverage and so on. We could go out to the web for all these reports, weather reports, major event schedules. We could grab a large map of road topology and properties. Every single road is captured. And of course, day and time. And build a large database that we could then use to make predictions. And we could use that Bayesian structure search to build out one of these graphs that will tell us, for different parts of the highway, the likelihood of a clog, for example, and then field it on portable smartphones, of course, people's pockets. and provide this kind of an inference here where you see this little wedge here showing the max likely time that a jam will last until it melts, as well as the system's confidence. So the system's reasoning about its own confidence and sharing that with people. And it was a lot of fun and exciting to build this system, but we also started learning about the value of these systems in people's pockets. Well, what did people use them for exactly? It turns out that most people in Seattle fashion themselves as Seattle traffic experts. They don't need to have inference to tell them it's a rush hour on a rainy night going to Kirkland from Redmond is going to be packed and terrible on the 405 North. So we actually started thinking about a user perspective on machine learning, which is a machine has a world model, and it's making inferences, for example, about traffic. A human being, this Seattle traffic expert with lots of experience, is looking out, and she or he have their own inferences. And could we build systems that could have a model of what people thought, and then consider an estimation or approximation of what people think and what it thinks is per gold standard, and work with people to share most important information possible? This led to our work on models of surprise. Can we learn with machine learning algorithms what will surprise people now and in the future? And the idea here is we have a human forecaster who understands major events, weather, time and day, and holiday or not. We could take slugs of 15-minute segments of time over a period of years and build an expectation model, and then find these exotic flows and clogs in the highway, which are like 1 in 1,000 or 1 in 100. We can set the threshold. And then we want to store a database of human surprises about Seattle traffic in this case. Our system has a bigger purview about what's going on in the world, including accidents happening, the dynamics over time, sporting events that the expert might not know about, the topology of the road, and so on. And we can actually correlate the human surprises with not just what the system knows now, but what it might know 10 minutes ago or an hour ago. So we're going to go back in time now. And here's the core idea. Can we build systems that I can hold up one day and predict when I'll be surprised in the future? And so we went to machine learning with this. And now, in the same system, on the same cloud service, we overlay a surprise forecasting model that's humming along with the base model. And it knows that most people in Seattle would be blown away by this clog here at this time, for example, or here. And what this means here is that you will be really surprised in an hour that this will be wide open. Right? It's predicting surprises. So if instead of looking at your device and checking it, we can have a proactive device that lets the user per preferences set up and say, just tell me when I'll be surprised in a half hour on my route home. And this brings up the idea of a human dimension to learning. It's not just domain, it's also the people using systems. Now, that work actually on what's called SmartFlow led to a ClearFlow project, which was the grand challenge of can we take highway data and a lot of GPS data collected by people working with us, about 1 million kilometers throughout Seattle, our road warriors, and build models that could actually reason about unsensed roadways based on their personalities and topological connections in that big graph called the Seattle road system. And this work led to Bing Maps' current traffic system that's humming right now as we speak. Every few minutes, flows on 60 million streets across North America are being updated in these major cities. So if every street has a little probability on it and a certainty and a road flow, we can then generate directions. The big question around Seattle here is, do I go across 520, 90, or do I go around the top? And if you use Bing Maps or your Windows phone, this is all default now and standard. And I've gotten one complaint about this system from a senior engineer at Microsoft who came up to me and he said to me, it's giving away my secret. I get off and get back on again over here. And this is the standard recommended route by the system. So let me move to healthcare now. That's transportation. I've been really excited about the prospect of facing these high-stakes daily challenges in hospitals, working across cultures, medicine, computer science, and the notion of coupling prediction and decision-making. And this is with a team including former postdocs from MSR, Princeton and Stanford, and folks who work with at multiple hospitals. So about 3 years ago, there was a very widely cited New England Journal of Medicine article that said, from 2004 data, that 20% of patients who are discharged from hospitals bounce back within 30 days. And if you look at these costs as avoidable or bounce backs as avoidable, that's $17.5 billion of avoidable costs per year. We got access to data from a large hospital in Washington, D.C., top 10 urban hospitals in the United States. And they had a beautiful system that they've been ahead of the curve here collecting data for about a decade. For example, they had 300,000 emergency department ED visits of all rich information, including admissions, discharge transfer, labs, diagnostic codes, procedures, vital signs, and so on. So we actually said, let's see if we can predict a readmission. Is there signal in all this data? Considering about 25,000 variables with our machine learning tools, we built several different kinds of models. What this model says here is that I'm going to predict someone's in the ED and gets readmitted in 30 days, EDA 30, and the system discovers the kinds of variables it likes to use that would be most discriminatory here, including gender and diagnostic codes and visit gaps between visits at the hospital and so on, age and so on. We can then build what's called a receiver-operator characteristic curve, which shows how thresholds that we set on what the system tells us will lead to different true positive and false positive rates with a training set and a little test set that we hold out to build these curves. And you can show these to physicians and say, this is how well the system that I built will work on your data. We can also say, here are some features that have been pulled out by the system which describe the most discriminatory evidence. For example, the fact that a patient has been wrestling with a malignant neoplasm, cancer, or has a heart failure diagnosis. These are well-known challenges for recurrent visits to a hospital. But most people, even experts, wouldn't think that staying 14 hours in an emergency room or looking at all text in a record that the word dialysis appears or the word fluid appears would be bad signs for staying away from the hospital. But our algorithms could figure that out and leverage that information. And over the last 2 years or so, we've built several different kinds of models, including models that predict readmission in various kinds and various horizons, models that predict that a hospitalized patient will acquire a hospital-associated infection within 2 days or 3 days and so on. This is a big challenge in hospitals. And we also have built new kinds of models. Now you guys are all surprise modeling experts. We did a surprise model. We said, what's a good surprise model for healthcare? And this model here was one built from data of the form that leads to models that make predictions of the form. The ED physician is told, the patient you're discharging right now will likely bounce back within 3 days with a primary diagnosis that's nowhere on the chart. Do you want to look? And the system so we're reasoning about the borders of human knowledge here as opposed to telling experts what they already likely know. Last year, we translated this research into a real-world system, Amalga, going into the open world. I'll just mention a few comments about this translation, as it's called in the health IT industry. First of all, for tractability, we had to back off those 25,000 variables, looking at how well do we do with 463 of them, or 37, and look at these curves and performance trade-offs. We also had to worry about, can you really take the same system and pull a string in different hospitals and have it trained locally without experts in the loop? And that's still a standing question. In fact, Microsoft Research for every install gets these curves. That's part of the deal. We look at the curves, and we're in touch with the team deploying these in the early years of this. There's some people from Southampton here today. We just deployed in Southampton in the UK. So just I see you shaking hands there. Yeah. The system basically provides a probability of a bounce back. This is a record sorted by patients who might recur, come back to the hospital within 30 days. And the next phase we took this work was into this whole notion of decision making. And this is where we are now. We're saying, okay, what do doctors do with that number they're seeing, this probability of readmission? Might it be avoided? So we've been working with a whole set of physicians on what you might do differently. What are various kinds of programs and interventions you might take advantage of to reduce the likelihood of readmission? Turns out there's a literature of people trying this or that. I tried this post-discharge program of education. I worked with the family. I realized this patient had poor self-care because of their socioeconomic situation or psychology and so on. And the idea is we want to take this predictive model here, probability of bounce back given evidence, which might be 400 variables or 25,000 variables, and reason about a decision model, or create a decision model that can do the right thing under uncertainty that maximizes expected value or minimizes cost. There are a variety of ways to frame that decision problem. What I want to just mention today briefly, we don't have a lot of time up here today, is that I'm very excited about the notion of building a system from data that has a predictive model you've built with a machine learning algorithm, a decision model that might, for example, take as inputs how much money you might invest in a particular patient and what the promised reduction in readmission rate might be. And before you field that system, run it in the same way we would run our classifiers now, but now it's a whole data to decision to action pipeline with a train and test for the whole pipeline. And even if there's uncertainty in these numbers, and there's a lot of uncertainty in the medical community, run the whole system with those test patients for different points in the dollar reduced readmission rate space, given the uncertainty there, and tell the DC hospital, if you believe you have an intervention that will cost $400 that can reduce the readmission rate by 40%, when we run this model with the classifier running with all its noise and all its power, and the decision model, here's the total savings you might get, and read it off this curve. So we're actually computing the expected value of immersing a system in the open world before we deploy the system. And this work is ongoing right now with clinical trials being kicked off in the DC hospital here. I want to shift gears now and talk about another case study. This is this area of work on citizen science that we've been engaged in over the last several years is an exciting one for us in that it touches on several topics, including how do we deal with large-scale data in science, which is growing so fast that scientists themselves can't keep up with it. It's also an area for the science and the computer science that we're very excited about. It's called human computation and crowdsourcing. We have a track today that Ajay Kumar has organized. I want to highlight in the citizen science work in the particular study we're doing, our excitement about computer science principles and methods for joining human and machine intelligence together, as well as in one system having predictive models and decision making that plays several different roles. So in citizen science, volunteers are engaged to, for example, help tag galaxies, flowers to classify various kinds of objects, spot birds, for example, per season, even do things like discover new objects from astronomical surveys. And in fact, that's the area we're working in with the Zooniverse folks. We're working very closely with people who have actually been working on building citizen science platforms for classification and discovery in astronomy. And our Microsoft Research Connections folks have also, for years, funded these folks in their core effort. The motivation is simple. So here's an example. The Sloan Digital Sky Survey several years ago did an automatic survey of the heavens and discovered about, per the digital encoding, about 1 million galaxies, 120,000 quasars, and 225,000 stars closer in our own galaxy. And created it. They said, this is far too big for any astronomer to look at. Maybe we get people to help us classify these galaxies into different categories that we take a little training course online, and it might be whether it be a 6th grader or a high school kid or a junior astronomer that that goes out every night and tries to find the comet that might have his name someday. These people all could be very valuable to astronomy. And they created a system called Galaxy Zoo, which let people view these galaxies. And a data set came out of this study of nearly 1 million galaxies, 34 million votes as to what people thought about these different galaxies, and engaged 100,000 participants. And this is work with Ajay Kumar leading up the effort, Severin Hacker, who was a CMU intern with us two summers ago. Chris Lintott, who leads up the effort in Zooniverse, and Art von Smith. To give you a sense for the Galaxy Zoo interface, here's what you face if you become a junior astronomer, or I should say citizen astronomer, because you might be senior as well. You look at a blob identified by the Sloan Sky Survey, and you try to classify it after you take a little course. Even classifying whether it's a clockwise or counterclockwise pinwheel and so on. A star, maybe you found a new object, for example. Now we noticed that there's also the Sky Survey itself was available. We could actually gain access for every one of those blobs, most of which were unforeseen, never seen before by human eyes, an automated machine vision-based survey of that object. And these are just a sampling of what these look like. Petrosian magnitude colors, Petrosian radius, inverse. These are almost, it's Latin to people outside of the astronomical field that what the camera is seeing. So we said, I wonder, can we build methods using machine learning and decision making that would fuse human and machine perceptual effort? We want to join those together. At the same time, we want to optimize the whole process by which how galaxies are routed to people based on their abilities and the need for votes versus a stopping rule saying we have enough votes and enough imagery on this object here, the celestial object, let's move on to another one now. So the idea of optimizing task routing and stopping. And so with a system called CrowdSynth, and now Zion, which is its descendant for a real-world platform, we basically said, let's break this problem apart into pieces. Let's think this through. We have a machine perception system that's going to look at the sky, take the Sky Survey data, these several hundred features. We have people who are now trained to do votes, and we have imagery flying by. Can we both fuse the information from both the cameras and people's votes with their own perceptual systems after they learn how to classify galaxies, and optimize where votes go and where objects go so that we can actually make the best use of people? Now, it's the people who are the scarce resources here. The camera can run all night and doesn't mind about whether it's 1 million or 2 million galaxies. So we went ahead and ran these models, and what you see, this is a little hard to decode, but the important part about this model we built in this case, and this is only a piece of the model, there are many more variables actually, this is the most important ones, is we're fusing together features from the camera with observations about the workers and their voting over time, given different objects, and current status of votes on this particular object, to generate probabilities of what the actual reality of this system is for this galaxy, when the true answer is known, as well as what the next vote will be. Now, you need both these variables to run a decision-making system that does sequences of actions and makes decisions about where to distribute attention in the system and when to stop. Now, just to give you a sense for how powerful this methodology is for the future of citizen science, and this should give you a sense for where this is heading, what you see here is the accuracy on the system with all votes in. There's a little cost-benefit information here because we looked at cost, even though most Galaxy Zoo people come on for free. But we looked at different pricing. But the idea is with the CrowdSynth algorithm, with just about a little bit more than half of the votes collected we showed, you can get almost complete accuracy. So the future in this work is we can actually start thinking about how to, more generally even beyond citizen science, how do we join human intelligence and machine intelligence in ways that make the best use of people and the best use of machines? And by the way, as the machine competencies are evolving, the border will be evolving as well. And we have several projects in this realm. One last comment about citizen science is this model here shows in a separate study that Severin Hacker and I did when he was an intern, how the correct answer coming from a particular volunteer is influenced, is predicted by what the computer vision algorithm tells us about the blob, what the experience is we've seen over cross-session with this user in how well they've done and being correct and incorrect in their work before, and even their current activity, their current dwell time, how long they've been on, how many objects they've looked at tonight, what time of day is it where they are in the world. Now, think about the implications of this. Here's a volunteer in this case, and we're going to reason about, for any object in the system, whether this person would be helpful or not. Now, if you think about it, one thing we could do is we could route tasks that are most effectively solved by that person, or most efficiently, let's say, spiral galaxies, to this volunteer. But even more interestingly, which is implications for online education, let's take examples of celestial bodies that this person does not do very well at. Could we have machine learning and decision theory guided educational experiences that focus on making that person better at just the places they're not good at, we found through online volunteer activity? So there's implications here also for education, online education systems that might someday build models like this beyond citizen science. So in the last case study or effort I want to talk about, I want to focus on the dream of building richer machine intelligences. There's some great quotes. Rick Rashid recently gave a talk, and he quoted what Marvin Minsky said about 5 or 6 years from now, we're going to have, we're going to basically replace human beings with all the intellectual and scholarly activities they do. And this is back, I think, in 1968 or something, Life magazine article. Even Herb Simon, who many of us know and knew and deeply respect for his contributions in core organizational behavior and artificial intelligence, thought that we'd be much further along by now. It's taking longer. I think we're on our way. One approach to this dream on our group, and we have some sister groups at universities right now, is intelligence via composition of competencies. I'll mention that as a theme here, as well as what you learn when you try to field systems that are situated in the physical world and that are taking action in the physical world. This work is with Dan Bohus, AJ Kamar, Ann Loomis Thompson, and Paul Koch, and several others on the team. So the basic idea of integrative AI is you say, well, there's been great advances in NLP. Some people here just got back from ACL in Korea, amidst the monsoon there. We have great work in planning, inference, learning, vision. The latest advances of these different kinds of, you might call them pillars of competency of a larger intelligence or intelligence system, are typically revealed in conferences like CVPR or ACL or ICML, UAI or KR. And the idea is, could we get further ahead by trying to take the best of breed of these areas and weave them together, where we might see that the whole is more than the sum of the parts, and might even learn about the integration, about the synergies and dependencies. So the Situated Interaction Project really takes as a perspective a pretty audacious goal, and it is, when people work in teams together, what would it be like to build an intelligence that's a team member? For example, in a complex surgical setting where there are multiple collaborators. Someday, technologies that can understand a group in front of a billboard and work with a group in interesting ways. Or imagine a system that you're using in your kitchen someday that is ambient, and as you're going through a recipe with a friend, you're being assisted. Go ahead, pour it now slowly. It's just tracking the the physicality and the goals and intentions. Or who has young kids? Imagine going out to the movies and saying, oh, no problem, I'm leaving the kids with Robo, and he's going to engage them, a little bit of education. We'll get a call if there's a problem. So to start this project off a few years ago, we actually set up cameras with disclosure and signs in our lobby at Microsoft Research Building 99. And just to get a sense for how does a receptionist work with multiple people coming in and with tasks, could we build a system that might be like a receptionist someday. In particular, this study was situated interaction with multiple parties at once in a dialogue system. And after looking at some videos and thinking this through, how do receptionists work with people that want shuttles, for example? How does he or she find out who's together, for example? It led to us thinking about representations that were fairly rich and over time, they have temporal dynamics, looking at joins and people in and out of the frame, tracking goals as they might be morphing over time or remaining stable, suspended goals, multitasking in these environments, even social graces. For example, when somebody walks in, even though you're busy, and the receptionist might nod and say, like, wait a second, I know you're there. And beyond the software and representation, we started thinking through, let's build a kind of a representative platform. Now, some people have seen this video before that I'll show now, but we built our first approach was to try to see if we could do some of the things that a receptionist does. I'll show a snip of this video with this kind of context, where the red dot is where this little avatar is looking. And this was our first go at this. And just watch how the system is recognizing multiple people and working with people that are not part of the scene that are coming into the scene.
Do you need a shuttle?
Yes.
Which building are you going to?
I forget, where are we going?
I think it's building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for building 9 for 2 people. In case you want to correct anything, say or press star over. Are you visiting someone?
Yes.
I'll help you register in just a moment.
Okay.
Excuse me, sir.
Yes?
You will be on shuttle 53.
So that was an initial foray, and we used that to figure out the competency and the gaps and problems with trying to work in the open world. One thing that was kind of delightful is that we realized that people weren't used to systems that could see multiple people and engage a group, and that was almost like startling and magical to people, and it frames the direction we're heading with computing in the world being more social. We did things like studies with users brought in with a usability program for example, how could a system, this is like, you might say this is not Jeopardy, Watson style, this is where we're trying to be Alex Trebek and understand how that works.
Next question. Libya is the only country with a one-color flag. What color is it?
It's a green.
Do you think the same?
Yes.
That's right. So far you have one correct answer. Now on to the next question. In the USA, hospitals have a Red Cross. What sign do they use in the Arab world?
What's that a red cross? What's that used in the Arab world?
Solid blue circle.
Is that correct?
No.
So what's the correct answer?
Anyway, we can really learn a lot about how a moderator might work with people in a social setting by watching how they work with each other, whether they're talking to themselves, to the system. Lots of learnings there. We actually also set up systems in, like by coffee hours at Microsoft, people could win a prize by playing this trivia game. We have great footage that's again filmed with disclosure, and learned a lot. Now, the current focus of our work in this area is called the assistant in terms of a platform. Let me show you what I deal with in the morning. This is my normal morning coming into work. By my office here. I just filmed it last week.
Hi, Eric. No one has stopped by to see you since we last talked. And Outlook Mobile Manager is still down, so I'm not seeing messages from your email. Catch you later. Bye-bye.
Now, this assistant is building on the same platform now. It's a really interesting set of tasks to support Eric and people that come to see me, given my calendar. But what's interesting is we're leveraging components that don't get old even when they're 6 or 7 years old. We presented the coordinate research at UAI about 8 years ago. We built a system that can reason about and forecast a person's presence and availability over time, even what time, how much longer until they read email, until they're in their office, if they're conversing, how long will the conversation last. This system has been running straight for about 8 years. And we said, we're building a platform to be an assistant. Let's give that system, as part of the integrative intelligence, that component. We also had a system called Busybody that can, in a separate piece of work that was published at CSCW about 5 years ago, that reasons about attention and interruption, and that can teach the cost of interruption at any time. And let's give that competency to the assistant. So let me show you a little bit about how the system works. There's a couple of vignettes here that capture how it runs.
So who did the GMP taping again?
Each vignette captures a different notion here of what it's doing in competency.
Okay. Oh, Derek, he's not around.
Are you looking for Eric?
Yes.
Are you Dan at home?
Yes.
I'm his virtual admin. I know he has a meeting scheduled with you, but he's late from his previous meeting in building 34. He's no longer on his laptop, so I expect he'll be back in 10 minutes or so.
Okay.
You can go ahead and wait in his office if you'd like.
Oh, we'll come back in a minute.
Okay. I'll make sure to let him know when he returns.
All right, thanks.
See you soon.
So this is Jeff, right? Jeff, go. Okay.
Hello.
Hi.
Are you here looking for Eric?
Yes.
Eric is having an impromptu chat right now, but I expect it should be over in around 10 minutes. Would you like to wait for a bit?
Sure.
Sounds good. He shouldn't be too long. Guess I'll see you later then. Bye-bye.
Bye.
Hello.
Hey.
Are you here looking for Eric?
Yes.
Are you here for the 2 o'clock meeting with Eric?
Yes.
Are you fan legal in?
Yes, I am.
Great. Eric is expecting you. Will you be joining the meeting?
Yes.
All right. I'd let Eric know you'll be joining his meeting with Dan. If you don't mind waiting around for a few more minutes, I'm sure he'll invite you in shortly. Yes, I'll see you later then.
So these scenarios go on, and they're quite rich and interesting. For example, I think in one scenario, someone's trying to schedule with me, and my schedule's blocked for the day. But the system using coordinate says, I don't think Eric will attend the meeting at 4 o'clock. I'll pencil you in, but like without telling me that what it's doing. And it has a Bayesian model of meetings that I'll attend versus not, even when they're on my calendar, something we all might find useful. And also has a nice reminder model and knows what to remind me about, like meeting rooms and so on, that runs with the system. Beyond the alchemy of cobbling these systems together, it really resonated with the dream of learning new things. And if you look at our stream of papers and results on this, and it's been a cauldron of innovation with interns over the last several years. Great interns have worked on this system. Steph Rosenthal was here last summer from CMU, and others. But the idea basically is we're learning about the whole notion of things like information value, which is a decision theoretic concept in streaming settings. How do we learn and combine multimodal streams that are unfurling over time, and so on. So I get really excited when we can take a hard challenge and learn new things and new core computer science results while trying to build a system that works in the real world. Let me just say that the same platform right now just got hooked in last week to Microsoft Building 99 elevators. This is the same situated interaction platform, slightly modified, that is promising to make the Microsoft elevators in its lobby like Star Trek doors. both opening when you walk up to it by recognizing intentions, and even holding the elevator door open when someone runs to catch it without requiring you to jam your leg or arm into the doorway. It's a 20th century concept. And it's kind of interesting. You think about the hard part of this problem. We already had our platform. The hard part of the problem was the Otis elevator guys, the Tyson Krupp guys, and Microsoft real estate and facilities people. You want to talk to our interface? Let me see who you might ask. And this is a very interesting challenge, but we solved all the challenges. We blew a fuse last week, hooking things up, an actual old-fashioned fuse. But we're now at the point where we're learning from those button clicks, or that supervised learning signals of the future. So I'm going to end by just mentioning just a real tiny bit about a very important topic. It's a whole other lecture or talk or conversation that we should all be having about privacy, data, and machine learning. During my talk, you've probably seen medical data fly by. You've seen people walking in lobbies of buildings. You've seen volunteer astronomers being rated for their competency behind the scenes. There's an urgent need for us to tackle as a computer science community and associated communities, the challenge of privacy data to get the most out of machine learning, both for a variety of applications. So it's an urgent area, but I'm very optimistic. I think this is not. I don't see doomsday here. In fact, several great pieces of computer science work are coming out. Some architectural, some in the HCI space, but others in notions of decision theory for managing the costs and benefits of sharing information and making that clear to people, along with controls. Differential privacy, notions of adding various kinds of distributional noise, Laplacian noise, and proving that it's okay to do that, bounding the error in answers. And a notion that I refer to as protected sensing and personalization, which is growing in interest at Microsoft, in Microsoft Research, and in other centers. We have colleagues at Stanford, for example, Monica Lamb, pursuing this kind of work. With protected sensing and personalization, the data mining center is owned by the user. It's their own stuff, and they can share all sorts of interesting nuances, all their email, for example, and all the reasoning, decision-making occurs within the borders of somebody's own devices. Several example demonstrations and prototypes over the years really resonate with the notion of this protected sensing and personalization. Several years ago, Jamie Tivon and Susan Dumais and I, actually when Jamie was still an intern at Microsoft Research from MIT, and one of David Karger's students, thank you, David, for giving us Jamie, it worked on P-search, personalized search. And with P-search, the idea was that a system would grovel over and index and look at email, documents, web activity, even GPS, Wi-Fi, and accelerometer data someday, build a local store of that information to run a personalized ranker. And when you did a search, for example, I did a search for Lumiere, the Bing engine would bring back a whole bunch of results. And the personalized ranker, in the secrecy and confidentiality of one's own computing world, would do a re-ranking based on the context and interests. And so, for example, if I put Lumiere and I get all the stuff about Lumiere Restaurant and Lumiere HD, but the personalized ranking would give me what I was looking for based on my email store and what I've been talking about and what I've been doing with my documents. And one other example is Life Browser. Richard Feynman said there's a lot of space down there when he talked about nanotechnology. Well, there's a lot of room for innovation and data mining with one's own stuff that we barely scratch the surface of. Life Browser crawls over your hard drives, keeps all its inferences as private, and then generates big timelines across multiple streams of information, with the notion of a memory landmark, the idea that I can do inferences about what things are most important and a volume control to go to the most important things or to everything. Again, all being done in the privacy of one's own world. And there's a lot of work that can be done in this space and in combination with cloud services that will bring a lot of the power of machine learning to life for people. By the way, Life Browser just runs active learning. Once in a while, even has a dialogue about memorable landmarks. For example, it asked me, is this PhD oral exam that Stephanie Rosenthal had, was that a landmark? And so I could say, oh, yes, that was, and the system gets better and better over time. But it's all done in the privacy of the box. Same with pictures and images with active learning. So let me stop there and take some questions. I'm just going to summarize that the applications of sensing and learning and reasoning are still very much in their infancy. I've mentioned the 4 studies with some themes. I think I see unprecedented value coming to people in society from these methodologies. And what we love to do is take principles, try to field them in the real world, and we learn new principles, and the cycle continues. So I'll stop there. Thanks very much.
Sir, if you would hold it up to your chin.
Hi, this is Kemal Ebcioğlu from IPIP Working Group and also Global Supercomputing. Now, there's been a lot of efforts in machine learning, like inductive inference, genetic algorithms, and the basic idea is you get and you create an algorithm for classification. And you can use that algorithm to actually classify data, or you can use that to generate a certain class of data, depending on the algorithm you created. But the results tend to be too simple for certain categories of goals. For example, try to learn beautiful music, try to learn what beautiful poetry is, or try to learn what beautiful mathematics is. And another approach is basically you handcraft the algorithm, and you use that to create the music. That's also very difficult. I mean, Doug Lennet tried to do that in math. Others have tried to do it in music. Mm-hmm. And the net is that the algorithms are way too complex to what the machine learner produces. I mean, is the model adequate for the lofty goals? I mean, or is it too simple so that it's really bounded on what you can achieve?
So I hear what you're saying, and I resonate with this idea that we still are early on in our ability to do many wondrous things that people do. That might be true forever. On classification, though, I have to beg to differ about the power of machine learning to learn the nuances of the essence of humanity in a way sometimes better than people can do. For example, understanding from a large corpus of voicemails which people, when they call me, know me well. I wouldn't myself, I could point that out, but I wouldn't be able to sort of write down any rules about that. And a system figured that out by listening to prosody. Now, it takes a training set where I say, well, I know these people really well, and these people I don't know well. And the system figures out, for example, in my case, that the maximum duration pause in an incoming voicemail message was pathognomonic, as they say in medical school, but was discriminatory for someone who knew me very well. All the work we see on sentiment going on the web, can I figure out what the sentiment is in text? So sometimes we find that surprising outcome of defining some audacious goals with data sets that are tagged to give us the information we need for algorithms to go through and find, for example, the one word, fluid, in the medical record, which physicians wouldn't have figured out was not the best sign for staying out of the hospital. Now, generating is a different story, but I'm very optimistic. But I did disclaim that we're in the early days of all this, and so I appreciate your question.
Okay. Okay. Thank you.
Okay. Any other questions?
Eric.
Yeah. Oh, I see over here.
Jim Hendler, Chair of the Computer Science Department at RPI. Come over here.
Oh, there you are, Jim.
There's the big number 1 up here.
Yeah, 1 helps. Yeah.
You know, Eric, you mentioned some of Jamie's work. You mentioned some of the other work you're doing with very large data sets and large pieces of information that can't be shared outside the walls of the building. And I guess really I thought, since Tony mentioned this as one of the themes, the whole issue of collaborations and things, is there any new thinking? Are there new ways we can be approaching how our students are going to learn to do the kinds of things you're saying at scale without somehow finding a way to create either modeled data sets or something that can be worked on jointly between us?
So my first reaction is, per that ambient data I mentioned earlier, there's a lot of large-scale data out there now, public that can give students lots of exercise in working these methods through. With the same data sets, a lot of undiscovered paths. Twitter feeds, for example, it's just full of such richness. It's very exciting to look at, even keyhole at a time, onto that massive data. There are a variety of initiatives underway. For example, in healthcare, the Center for Medicare Services is working to set up a whole data office focused on sharing with the academic community. How are they going to solve the HIPAA challenges and so on? It's up for research right now, maybe new legislation. Microsoft Research Connections, Evelyn, is Evelyn here? Worked on a program to share out Bing search logs when they were appropriately cleaned, sort of managing that kind of bias that might be introduced in the analysis, but actually licensing that with a licensing program to academics who showed up a couple times with really fabulous results and programs and workshops about that data. So I do hear the pain in not being at a place like Microsoft with massive feeds coming in that we have access to. We have programs underway, but also send us your best interns. Yeah.
So it seems to me that your research has always kind of had sort of significant privacy implications, and I guess how you've managed that in the past is by sort of balancing utility and privacy at the same time, right? Maximize utility as much as you can. Can you tell me about the principles you've used for achieving that balance?
Well, most of the work we do would involve privacy incursions does not impact the outside world. They're prototypes typically and so on. For those that do, we've come up with new approaches. So for example, Ryan White and I just published a paper on looking at mobile phone data that happen to have GPS on it. We actually, in a very early stage of our analysis, removed all GPS and just looked at absolute distances between hospitals and that phone. So there are a number of variety of mechanisms that can be used for that kind of thing, where you can get some remarkable results with data that would not be identifying. Back to the utility question, I should say, more generally, I believe there's a lot to be learned and a lot of opportunity in designing systems that figure out what's the most useful information to optimally provide a personalized service, for example, to users, that's least invasive per preferences of the user. And Andreas Krauss, one of the fellowship awardees today, worked with me when he was an intern at Microsoft on a piece of work that really lightens my heart with possibilities for really addressing the hard problems of privacy. Because it showed, using some of the really nice concepts that Carlos Gestrin and Andreas developed of submodularity, that you can actually find really non-invasive pieces of data and inform people about them that were quite ideally discriminatory. You didn't need everything. So I love the idea of being able to make that trade in our system someday. We have a JARE piece on that online if you want to read about that. But in general, we think hard about privacy. We also have a privacy officer. We're thinking of setting up an ethics board of our own, like an IRB of our own, for research purposes. The Microsoft people here in the audience will remember an email I sent last week that was the result of several conversations with our legal team, with our privacy folks, and with researchers and the Office of Directors at Redmond about what would our policy be at Microsoft Research Redmond about putting a sensing and learning prototype into a lobby or the elevator. How should we handle that to do what we call dog fooding for the sake of research? And we put in place a certain set of procedures, including the ability to opt out through an anonymous email to an anonymous site. I hope I answered several dimensions of your question, which you implied in your question. Yeah.
Yeah, I have a question that follows on that. This is Edward Hovey, still at ISI in Los Angeles. So as you put together the individual functionalities into increasingly sophisticated services, and as you embed them into society rather than just give them to scientists and things, when things go wrong, it seems to me more and more people are going to get angry, not just at Microsoft, but at that particular thing. If your personal assistant tells me, oh, I have to wait for 15 minutes and I see you in the office doing nothing, I'm going to get pretty pissed off. So when we see a real person there, we do something about a certain agency and responsibility. When we see a piece of software there, we as computer scientists, we don't care. We just say, well, the thing is screwing up, right? But increasingly, it seems to me, maybe Microsoft is going to have to large corporations that make many different software products is going to have to create some kind of agency with legal responsibility for each product separately, saying my personal assistant software has a certain legal persona which is different from my car helping software, which is something like that. At least I can imagine that's the way the world would go. Is there any discussion of this kind in Microsoft?
So there's always reflection about the implications of new kinds of automation. There was a fabulous NPR piece last week about FDA getting interested in regulating medical apps on your devices. Because aren't they making decisions, then aren't they be taken seriously, and so on. So there's always been an interesting border between, there have been different perspectives, and these evolve with technology and society. Back into privacy, I have to just say this again. We studied privacy quite deeply here. Interesting to see Benjamin Cardozo at the Supreme Court making comments about, in the late 19th century, about flash photography causing privacy incursions, or in the 1920s, discussions about, would we ever allow someone else to ring a bell in my living room? This newfangled thing called the telephone. And now it's in our pocket. Oh my gosh. So I think things will change over time in terms of what we expect and failures we tolerate. When it comes to my agent by my door, I think Ed muttered, which one's a tight ship. But no, not that tight. People just walk around or something. They come see me anyway. So not to worry about that piece. But yeah, I think people are very interested in policy implications, societal implications, psychological implications of technologies at Microsoft. In multiple product teams and in research.
Hello, this is Luis Sazzi, University of Washington. Thank you for right here, number one. Okay, thank you for a great talk. So I was just curious if you could tell us a little bit about what do you think are the technology or other challenges to push this to the next level? Is it the quality of the data? Is it the amount of compute power? Or is it the algorithms? Or what do you think are the big technology challenges to push this further? So,
wow, what a great question. And by Max, you're talking about things like the assistant you saw at the end.
What is that? So I was talking about machine learning.
More generally?
Yes.
My sense is, to be fair, all those things you mentioned, I do think that computational power and memory and connectivity and sensing will have had unexpectedly great outcomes in terms of the boosts we get in things that we look at as intelligent. There's still a lot of headroom for algorithmic work. Every once in a while we get surprised. Submodularity, I think, was a surprise. I'm looking at Andreas Krauss right now. We used to do things, we thought they were heuristics, and we found out later that maybe they're they're well-founded. With Nimehouse's result, for example, or the work that's happening right now in the deep belief networks, deep learning, cascades of variables where one layer is doing inference, becoming the input to the next layer. There's some interesting magic to be decoded there. And some of it may be related to and have influence on decoding us, what's going on in our own cerebral cortexes and the rest of our brains, which excite people as well. Those results, I think, are still fundamentally mysterious. Mm-hmm. And nobody has a really great understanding of what's really going on in terms of why we're seeing better results than with prior methods. That leap I showed you with Bing Mobile Search, for example, is quite surprising to me personally. So I think all of them, algorithmic headroom, but really celebration of the power of the computation, the networking, and the memory. Last question.
So this is Sumesh Jha from University of Wisconsin. So I wanted to revisit the privacy aspect. And
I'm glad I included a slide on that.
So one thing that I find generally in the research side is that people don't understand the implications of sharing data. For example, if I'm a scientist and I want to share data to collaborate, do you have some thoughts on how do you make somebody who's not a machine learning expert or a computer science expert saying, okay, if you share data in this setting, these are going to be your privacy risks or implications? Or do you think some of the techniques could be helped there?
Yeah, this is one of the reasons why Cynthia Dwork, who works in differential privacy, and Frank McSherry like that methodology, because even with repeated queries to a database, they can say things about the extent of the risk. You're bringing up, honestly, a fundamental and hard challenge, which is communication, even the entailment, what it does mean when you, for example, share information over time, in particular, in multiple episodes of different forms, even entailing what that means, and then describing it to somebody with caveats. To me, I'd like to end this meeting by saying that's a really hard challenge you just brought up. I have some faith in our HCI folks and in controls and combinations of the methods that I mentioned to address those issues, but the way you just framed the challenge, I think, poses some of the hardest problems for privacy. I'll stop there. Thanks.